Shoot.
I hate this.
In my director reading about it, I also realized that I'm at full book of energy solitude. So I'm like, okay,
Okay.
Astro, Saturday, philosophical theory, no.
So, problem set 1, due tomorrow, right? 4 o'clock, please. Not 4:30, 5 o'clock, okay? 4 o'clock. And then here's problem set 2, which will be due next Friday. I got the date correct on this one. Okay. Like that. And my question.
When we turn in the hard set, do we also turn in that piece of paper?
You don't have to. If you want to have an entire, a complete packet for your own future use, that's fine with me, but you don't have to. Okay? My operating procedure is that I grade these over the weekend, or at least I get them done by Tuesday, so that you get them back the next time we do. And that I will post a solution, which you can then go and cross-check with your graded work and make any kind of, course corrections that you feel like you need to do. Okay? And also, you can ask me any questions about the homework. So this would be for stuff. And, is it somebody else?
Stop.
Okay.
I'll be here in
We're going to make 2 extra. I always make 1 extra for me, but I don't mind have 2 extra. Okay, doesn't matter. All right, any other questions about logistics? Okay, we're going to continue talking about ideal gases and the first law of thermodynamics and the equipartition theorem. Okay. But before we do that, I want to start with a demonstration. Okay. And this will involve the ideal gas law. Let's write it in this form. Remember, there are 2 forms you can use, depending upon whether you use the number of moles of gas, little n, or the total number of molecules, or atoms, big N. Just be careful to use the correct constant, depending upon which way you go to measure how much stuff there is. Either number of moles or number of particles. This is called the gas constant, and this is called Boltzmann's constant. Okay? That is a good model for any dilute gas. Okay? And so let's apply that to a gas that consists mainly of water vapor. Now, I do this demo in intro physics, but it's fun. So we'll do it again. Okay? So what we're going to do is we're going to light up the old Bunsen burner. Okay? And then I've got here, depending upon what part of the country you're from, a soda can or a pop can. And I've put just a little bit of water in it. Okay? Or a little bit of water in it. We're going to hold it over the flame. Okay? That will provide energy as heat into the water in the can. The water will quickly heat up to 100 degrees Celsius. Then we're going to keep adding energy. It's going to undergo the phase change from liquid to gas. And we're going to end up, and when it does go from liquid to gas, it expands to fill the rest of the can as a gas. So we'll have a can with predominantly water vapor, maybe a little bit of liquid water at the bottom. And then I'm just going to invert it so that the open end is immersed in the water here in the beaker. Okay? I got to make sure I've got water vapor in there. Now you can see it coming out of the top, yeah? Oh! Wasn't enough. All right, I didn't wait long enough. Let's try it again. Make sure we got full water vapor. All right, so we want to understand why that happens. Why does it implode on itself. So dramatically, sending water all over the tabletop. Why does it do it? Let's think about what happened there and apply the ideal gas law. Okay? So imagine I'm holding the can with the open top over the flame before I put it in the beaker. Okay? Let's go through and let's think about what we know. The volume of it's filled with water vapor in there, right? The volume of the water vapor is pretty much the volume of the inside the can. Okay? All right? What's the pressure of the water vapor? What do you think? When I'm holding it, just holding it over the flame, right? It's open here. It's got to be atmospheric pressure. It's open to the atmosphere, right? Atmospheric pressure. There are some number of moles. You can estimate how many it is for that size. It's not very much, right? But that still means there's a lot of water molecules zipping around. What's the temperature of the gas? What do you think? What do you think the temperature of the gas is? The water vapor gas. If there's still water, let's say there's still a little bit of water in the bottom. What's the answer then? It's 100, right? Because it stays at the phase change temperature until all the material has changed phase. The trick then is to get that just before the water is all gone to vapor, and then the vapor, if you still add energy, the temperature will start to go up. Okay? But if I can get it so that there's still a little bit of liquid water left in the bottom, and then the rest of the can is filled with water vapor, I know the water vapor is at 100 degrees Celsius. Okay? So I know the T, I know the P, at least initially, I know the V. And I've got some number of moles of water vapor in there. I estimated it's a fraction of 1 mole. Okay? But it doesn't matter, it's a lot of molecules. Then I invert it and put it in contact so that the open end is immersed in the water. Right? And you see what happens. So it implodes because, well, why? What's just the most, how would you get something like that to implode? Pressure. Pressure is important, right? What's the pressure on the outside of the can? Atmospheric. So the pressure on the inside must be what compared to atmospheric? It's got to be less. It's got to be considerably less. More than the aluminum can withstand. Okay? For internal, inward going pressure. So the pressure's got to be going down when I immerse the open end of the can in the water. So now let's think about why the pressure is going down. Again, using this. Why is P going down for the water vapor in the can? That's right, we've got, right? Because it's got to be applied to a gas. We've got to be talking about the water vapor.
This is escaping, speeding up and escaping. Okay.
When I invert that over, the open end, which is the only thing it could escape from, is immersed in the water.
The temperature goes down.
Well, the temperature is 100 degrees Celsius. I've got some water vapor in there. I immerse it in the water. Is the temperature going to immediately start going down? What's going to happen immediately? Will there be energy going in or out from the gas? When I took it right out of the flame, yes, and inverted it and put its open end in the water. Will there be energy going in or out of the gas? From the gas? The water? Because the gas is at what temperature? 100 degrees? Are the surroundings at 100 degrees?
No.
Less than 100 degrees? So there's going to be a transfer of energy from the gas to the environment. The environment is everything else. Okay? Okay, so energy is going to come out of the gas. So what's going to happen to the gas immediately? What's going to start happening right away? Not the temperature drops. Because the gas is at what temperature right now? 100, a phase change temperature. So what's the gas going to start to do? It's gone to phase change, but now going back from gas back into liquid. Okay? That draws a lot of energy out. Okay? So what does that do to this equation describing the gas? What changes? The volume hasn't changed until it collapses. We're talking about right before it collapses, right? got to go down, but that means something over here's got to go down. What's going down over here? We just said, it's not temperature, is it? It's got to be this, the number of moles of gas. Well, how's that happening? What's happening? It's, you just told me what it's going to do. You just told me. It's going to condense. So, am I not losing the amount of gas I've got? Yes. I'm losing gaseous water, and it's because it's starting to condense into liquid water. So what I'm losing over here is this. I'm losing gas. It's going away. That means the pressure has to go down. Okay? And it goes down pretty quick, as you saw, until it gets to a point where the aluminum can't withstand the inward pressure from the atmosphere. So there's a lot of interesting physics there, right? And it's pretty dramatic. And you see pictures in physics textbooks where things like that have happened with even like steel containers, okay? Where there's some pretty dramatic pictures in intro physics books with like railroad tanker cars. Those big steel cylinders that are on wheels, and that they used some kind of a steam water mixture to clean them out, and then they capped it, and then they let the steam condense. It was filled with water vapor. They let it condense. They lost pressure on the inside. There was atmospheric pressure on the outside. At some point overnight, while after the workers are gone home, okay, the steel railroad car couldn't withstand the pressure difference. It's the same effect. As far as I know, it's not named after anybody, okay, but it's that effect. All right, now so you can understand that with Physics 111 level. But there's a lot of good physics in it, so it's worth talking about again. So that's why I wanted to start with that. Okay? Okay, so what I want to do next, what I want to talk about more formally first today, is some practice applying the first law of thermodynamics, which remember is just a statement of conservation of energy. And we're going to focus specifically on a container with a dilute gas, which of course we will model as what we call an ideal gas. So I'm imagining the kind of container that I've talked about over here before, right, with a kind of a hot plate type device at the bottom where I can connect the gas to a thermal reservoir, and I can let there be an energy exchange as heat into or out of the gas through that thermally conducting base. If I want to, I can adjust the number of molecules of the gas through this valve, or I can fix the number of molecules of gas by closing that valve. And if I want to fix the volume of the gas, I lock this piston in place so that it can't move. But if I want to let the volume of the gas change, I take away the locking pin so that this piston can move without friction. And then I can adjust the pressure of the gas by fixing how much pressure is on the top side of the piston, because the piston will always move so that the pressure on top and the pressure on bottom are equal. And the pressure on the bottom side is the pressure of the gas. Okay, so that's our kind of standard apparatus. And we're going to be applying the first law of thermodynamics to a series of, if you like, experiments with that. All right. First thing we have to be clear on is, one of the things that's going to be important is that if the volume of this gas changes because this piston moves, then there's going to be work done on the gas by the environment, i.e. whatever's on top of that piston, pushing. Okay, so if the volume of the gas changes, there's work done on it by the environment. We need to be able to calculate that. Question?
Do you ever calculate the heat equation?
The what?
The specific heat?
Oh yes, we'll definitely talk about that. We'll be talking about that a little bit later today. Most likely we'll get to that. Okay? I won't need it for what I'm going to talk about in this set of slides, but we are going to be talking about specific heat capacity and specific heat capacity quite a bit. Okay? Now, it's derived in your book, the expression for the work done on this gas from an expansion or a compression, the volume change. Okay? Your author calls it compression expansion work from a volume change of the gas. Okay? There are other ways you could do work on a system. If you had an electric field in there and there were charged particles, you could be doing electrical work. Right? But for this container, this apparatus, the only work is going to be expansion compression work from a volume change. And if you integrate force with displacement, F dx, which is the way you calculate work, right? For a volume of gas like this, you get negative the integral of the pressure with respect to volume. You have to integrate the pressure with respect to the volume. And it's a definite integral, starting at the initial volume and ending at the final volume. And I write it this way, P, V in parentheses, to remind you that in order to do this integral correctly, you must know how the pressure is a function of the volume. You have to express the pressure as a function of the volume in order to be able to do that as an actual integral. Okay? And the negative sign is there so that work done on the gas is positive if the gas is compressed. Work on the gas is positive if the gas is compressed. Work on the gas is negative if it expands. Now here's another thing to remember. As is true with anything that's an integral of one variable with respect to another, if you make a graph and plot this variable, pressure, on the y-axis, and the other variable, volume, on the x-axis, then the integral is the area under the curve. So we'll sometimes draw plots of pressure versus volume for an experiment. It's called, when you do that, a PV diagram. It's just a plot of pressure on the y-axis and volume on the x-axis for whatever the experiment is. Okay? Then one way to think about the work done on your system is to say, well, first I just got to find the area under the curve. If the curve is simple, like a straight line, it's not too hard to just use geometry, find the area underneath. But then remember that you do have to give the work done on the gas the appropriate positive or negative sign. And that you have to just figure out by context, mainly. If the gas is being compressed, that would mean that the final volume is less than the initial volume. Then the work done on the gas must be positive. If the gas is expanding, so that the final volume is more than the initial volume, then the work done on the gas must be a negative number. You will know that from the context of a problem, whether it's expanding or being compressed. So we will use this a lot. Sometimes we'll just plain do the integral. Often we will. That's when we know P as a function of V. Then just do the integral. Sometimes we'll give you a plot of P versus V, and then you want to think of work as area under the curve with the appropriate plus or minus sign tacked on out front based on the context of is it expanding or being compressed. Okay. All right. So with that in mind, we're going to look at two different experiments with an ideal gas. No. First experiment with an ideal gas is going to be what's called an isothermal process. We have to be very clear on what we mean by these terms. Okay? We are talking about the gas when it's undergoing an isothermal process. Here is what we mean, and this is exactly what we mean, and nothing more than this. The change in the temperature of the gas is equal to 0. Temperature of the gas does not change. Isothermal means constant temperature. Make no other assumptions than that. Constant temperature. Okay? All right, let's see what the first law of thermodynamics and other physics that we know tells us about an isothermal process with an ideal gas. First, we will use the equal partition theorem to get the thermal energy of the gas. U thermal. The equal partition theorem says that for every degree of freedom, Each molecule contributes an average energy of 1/2 times Boltzmann's constant times the temperature. Well, let's say every molecule has F degrees of freedom, where F could be any small integer, for now. Okay? And that there are capital N molecules. So then the total thermal energy of the gas is 1/2 kBT times the number of degrees of freedom for each molecule F times the number of molecules, capital N. That's got to be the total thermal energy of the gas from the equipartition theorem. It's that easy. Note then that the thermal energy depends on the number of degrees of freedom, the number of molecules, and the temperature. Doesn't depend on the pressure, doesn't depend on the volume. Okay? Now, isothermal process means change in the temperature, 0, or the temperature is constant. So the thermal energy is constant. Thermal energy of the gas cannot change in this experiment. Okay? So delta U will equal 0. Okay? We know that from the equipartition theorem in this expression. All right? What else can we figure out? I haven't even invoked the first law of thermodynamics yet. We can use this expression up here for the work done on the gas to actually get a symbolic expression for the work done in this case. We're going to start right with that expression right there. But I must express the pressure as a function of the volume and then substitute that in here in the integral. Well, I do have the ideal gas law I can use. I'll take this form. I'll solve it for pressure, N kBT over the volume, and then I'll substitute it into the integral up here. So I'll have the integral, with a negative sign out front, of N kBT over V dV. Of course, I can pull any multiplicative constants out front. Just make sure the things that I pull out front are things that are not changing during the experiment. We'll assume that the number of molecules is not changing. Boltzmann's constant isn't going to change. And in this particular experiment, the temperature doesn't change. So you can pull the N, the kB, and the T out front. Then you have to recognize that as a famous integral. Integral of d blob over blob is the natural logarithm of the blob. Then put in the limits, use what you know about logarithms, and you get this. Negative nkbt log of v final over v initial. If you don't like the negative sign out front, you can absorb it into the logarithm by inverting the argument. And you get nkbt log of v initial over v final. I mean, either one of these are obviously mathematically equivalent. Note, if the gas is compressed, the initial volume is greater than the final volume, right? If it's compressed. That means the numerator is bigger than the denominator. That means the ratio is bigger than 1. That means I'm taking the log of a number bigger than 1, which is positive. Passes a sandwich. Okay. All right, so I know some things about the gas in this isothermal process. The change in the internal energy will be 0. And this will be the formula for the work done. W on will be positive if the gas is compressed, and of course it will be negative if the gas expands. Okay. Here are what the PV diagrams. I've drawn some example PV diagrams for this experiment, what they would look like. Now I chose to do the graph PV diagram in a somewhat specialized way. I didn't just plot plain old pressure versus volume. This is obviously volume in meters cubed. I plotted pressure over NKB. I just scaled the pressure by those two things because they're constant. That combination has units of Kelvin over meter cubed. And then you just use the ideal gas law. P over NKB equals T over V. T is a constant. So this is just going to be of the form y equals a constant over x. And I just plotted that for 3 different temperatures. That's just changing the value of the constant. Okay? And by scaling the pressure axis this way, if I make the graph for, say, T equals 1 Kelvin, that's the curve in blue, it actually goes through, when V equals 1 meter, 1 on that axis. If I plot for T equals 2 Kelvin, that's the curve in red, it goes through the point when V equals 1, 2 on the y-axis. And then here's the 3 Kelvin curve, and it goes to the point 3 on the y-axis. And you could you could draw these all the time, right? Over and over, okay? Each one of these corresponds to a different constant temperature. And so each one is called an isotherm, okay? And if you do have the gas expand, let's say we do our experiment along the 3 Kelvin isotherm, starting at a volume of 1 meter cubed, and the gas expands to 4 meters cubed in an isothermal expansion, then the process would follow this gold curve, all right, the T equals 3 Kelvin isotherm until you got to the final volume. Okay? Notice the pressure has to go down as the volume goes up, and the temperature is staying constant in this experiment. That would be an isothermal expansion. Okay? Now let's think about how much energy exchanged as heat is going to happen in an isothermal process. So now we'll apply the first law of thermodynamics. Change in internal energy equals energy exchanged as heat plus energy exchanged as work. But now let's put in what we've already learned from other pieces of physics. There is no change in internal energy for this isothermal process, for this system obeying the equal partition theorem, because no change in temperature means no change in internal energy. So that's a 0 in the first law of thermodynamics. If that's a 0, then just rearrange and solve the first law for Q. Q must just equal the negative of W on. It's just Q and W have to be negatives. If the internal energy isn't going to change, okay, but let's say the gas expands. If the gas expands, then remember, W on will be a negative number. Okay? Well, that's a loss of energy then, right? W on is a negative number, that's a loss of energy. But if the internal energy overall isn't going to change, then you have to compensate for that loss by having some energy come in from somewhere. And the only place you have available to you is Q. So if you're going to have the gas expand isothermally, it's going to use energy, that's the W on being negative, so you're going to have Q, you're going to have energy come in as Q. So Q is going to be positive. That's what the first law is telling you. Okay? You want the gas to expand so that W on is negative, then you're going to have positive Q. Okay? Or you could do it in reverse. You could compress the gas isothermally. Don't let the temperature change. That's an inflow of energy in the form of work. So you're going to have to take energy out as heat. So the Q is going to have to be negative if you don't want the temperature to change. Okay? So that's one experiment. Isothermal process with an ideal gas. Okay? Now let's talk about one that's a little bit more interesting or challenging. Note then what I just mentioned. I'll write it over here. Isothermal process, ideal gas, delta U equals 0. Okay? W on, not 0. It's either going to expand or be compressed. Right? From the first law of thermodynamics, if this is 0 and this isn't, Q can't be 0, right? Absolutely cannot be 0. So in an isothermal expansion or compression of an ideal gas, there must be heat going in or out. Must be. Absolutely cannot avoid it. Now I want to talk about a different experiment. This was an isothermal process. Now we're going to talk about what's called an adiabatic process. And it's very easy to get isothermal and adiabatic confused. Okay? So here's what adiabatic means. It means no heat is exchanged with the surroundings. No heat exchanged with the surroundings. That's what the word adiabatic means. No heat exchanged with the surroundings. That could happen for a number of different reasons. It might happen because the container is very well insulated, so that there just is not going to be any energy exchange to heat. It's got thermal insulating material over all parts of it. Okay? That's one way it might happen. That would clearly be something that we would contrive in a controlled setting in the lab. Or the process could just be slow enough to be quasi-static, that means everything's still well controlled, but fast enough that there's not enough time for the heat to be exchanged between the system and its surroundings. You get different kind of time scales here going on. It's possible for the process to be slow enough to still be well controlled, but too fast for there to be time for the energy to be exchanged with the surroundings. So either way, the whole process is over before there's a chance to exchange any heat. No matter how it happens, we're talking about a situation where Q equals 0. Because that's what no heat means. Q equals 0. Okay? Note that is not the same, necessarily, as saying delta T equals 0. Delta T is talking about temperature change. Okay? Here I'm talking about heat exchange, energy exchanged as heat, Q. So now we're going to go through and we're going to use the first law of thermodynamics and the ideal gas law, and we're going to see what we can say about this adiabatic process. Okay? I'm going to write the first law. I'm going to do it in the infinitesimal form for right now. An infinitesimal change in internal energy could in principle come about by an infinitesimal energy exchange as heat. That would be a dQ. Plus an infinitesimal energy exchange as work, dW. But if the process is adiabatic, by definition, the dQ term in the first law must be 0. It's the definition of adiabatic. No energy exchanged as heat. So I'm going to put a 0 in the first law for the dQ term. Now, for the dW, well, before, a little bit earlier, I wrote W was the negative integral of P dV. So if I'm just considering an infinitesimal version of that, dW, then it's just negative P dV. You don't have to actually do an integral when you're doing the infinitesimal version. So for the dW, I put in negative pressure times an infinitesimal volume change, negative P dV. So the only way the internal energy of the gas will change is if there's a volume change. Because there is no dQ. All right, now let's keep going. If the ideal gas obeys the equal partition theorem, and we'll assume it does, then we know the internal energy has this form: number of degrees of freedom, number of molecules, Boltzmann's constant, temperature over 2. Let me take the differential of both sides and write that as du, and the only thing changing over here in this experiment could possibly be the temperature. Temperature can change. Adiabatic does not mean isothermal. So du could be Fn kB over 2 times dt. And so that's what I write here for du. That's equal partition theorem. And then for negative PdV on the right, I'm going to use the ideal gas law. P is N kBT over V. And write the negative PdV is negative N kBT over V, dV. Okay? This is all physics we've now talked about. Look at this term and this side and this side. The NKBs on both sides cancel. And I have F over 2 dt, bring that t down and over, equals negative dV over V. With me so far? Okay. Think of this as a relationship between temperature change and volume change, right, for an adiabatic process with an ideal gas. Okay. If an ideal gas is undergoing an adiabatic process, an infinitesimal change in temperature and an infinitesimal change in volume must be related by this expression. And it does depend on the number of degrees of freedom that the molecules have. Now what I'm going to do is take this expression and I'm going to integrate both sides. We're going to do it as an indefinite integral. So when I'm done, after I do the indefinite integral of both sides, there'll be an additive constant, plus c. So when I do the indefinite integral over here, of course, that's just d blob over blob. So I get f over 2 natural log of the temperature. When I do the indefinite integral of this term, I'm going to get, that's another d blob over blob. So I'm going to get negative natural log of the volume. And then I just have an additive constant, because I did these as indefinite integrals. Obviously, I have two additive constants. I can combine them into one, though, on one side. Now let's just combine. This term right here with the f over 2 out front, you can take the f over 2 inside the logarithm, but then it becomes a power on the temperature. So now I have log of t to the f over 2 power equals negative log v plus a constant. Now let's take that term over. So now I have log of t to the f over 2 power plus log v equals a constant. Now use property of logarithms and write this as the log of t to the f over 2 power times v equals a constant. Now take the anti-log of both sides. And I get t to the f over 2 power times v equals e to a constant. I don't care what the constant is, so I'm just going to call e to the constant a new constant. Okay? In fact, I'm going to just write it like this now. T to the f over 2 power times the volume just must equal some constant for a given adiabatic experiment. This combination of temperature and volume is kind of a weird combination. Temperature to the f over 2 power times the volume to the 1 power. That combination will not change throughout the adiabatic process. Okay? By the way most books will write that is they will take both sides to the 2 over f power. If they do it to both sides, you can do it. Okay? Then the left side becomes t to the 1 power, v to the 2 over f. And the right hand side is still a constant. Might be a different constant than there, but the point is, I don't care right now, it's just that it's a constant. Okay? So this is the way you'll see most books write it. And you might even see the books write it slightly differently. I'll just tell you this part verbally. What you might see in a lot of books is where this exponent is here on the volume, 2 over the number of degrees of freedom. It'll be written as another symbol, gamma, lowercase gamma, minus 1. Where the lowercase gamma I'm about to define on the next slide. Okay. All right, this is very handy to relate temperature and volume if the process is adiabatic. Maybe what I'd like to know is how the pressure and the volume are related in an adiabatic process. Not T and V, but P and V. It's not hard to go from this to a relationship between pressure and volume. Just combine that with the ideal gas law again. Okay? So, use PV equals NKVT in the previous result. Okay? Actually, I don't need that line. I'm going to go right to this line. Right here. This second line. Where I'm going to use this result. Right here. You see where I have the T? Right here? I'm going to replace it with PV over NKV. See it right there? That was the T to the 1 power before, and it's multiplied by V to the 2 over F, right here. And that must equal a constant. So I'm at this line, okay? I went right to this line. Multiply both sides by NKV, still have a constant on the right. And now you have on the left P. And now look carefully. You've got a v to the 1 power times a v to the 2 over f. So add the exponents, right? 1 plus 2 over f. Get a common denominator. 1 plus 2 over f is f plus 2 all over f. And now that's the relationship you'll see in books relating pressure and volume in an adiabatic process with an ideal gas. And here's the constant I mentioned, the lowercase gamma. PV to the gamma power, that's an exponent there. PV to the gamma power equals a constant, where by definition gamma is f plus 2 over f. And it's called the adiabatic exponent. And notice that the adiabatic exponent gamma has to be bigger than 1. Because the numerator is f plus 2, and the denominator is f. The numerator is bigger than the denominator. F, remember, is a small positive integer. Okay? So we want to be able to talk about an ideal gas undergoing an adiabatic process. That means we can relate the temperature and the volume and the pressure and the volume with these expressions I've just talked about. Let's draw a PV diagram for an adiabatic process and compare and contrast it with an isothermal process. Okay? So pressure here, I just went with arbitrary units for the pressure, volume in meter cubed. I have drawn two different isotherms. In blue, that's an isotherm for a temperature T1. In gold, that's an isotherm for a temperature T2. I know the blue isotherm corresponds to a higher temperature than the gold one because isotherms that lie higher up correspond to higher temperature. You can think about that with just the ideal gas law. Okay? So these two are isotherms. They're basically here to guide our eyes in this graph. This isotherm T corresponds to T1 being bigger than T2. Now let's just say for right now that the gas undergoes an adiabatic expansion. So the volume starts, say, at 1 meter cubed and ends up at 4 meters cubed. So we will start at a temperature T1 to start with. So we're going to start right there, you see? We're going to start right there. And we're going to let the gas expand, but no heat can go in or out. Q equals 0. Okay? Then how do I make, what do I plot? Well, it's got to follow this form, right? It's got to obey this. P v to the gamma power equals a constant. Or, rearrange, P equals constant over v to the gamma power. Yes? And gamma, the exponent, is bigger than 1. So this is of the form y equals a constant over x to the gamma power where gamma is greater than 1. Right? That will fall down, that will come down faster than c over x to the 1 power, which is what an isotherm would do, yes? So the T1 isotherm comes down like 1 over v to the 1 power. So the curve for this adiabatic process must come down more steeply than that. So the point is, it has to fall below the T1 isotherm. It has to come down more steeply than the T1 isotherm, just from that function right there. And then when I get to the final volume, actually I'm going to go out to 5. I'm going to go out to 5 meters cubed. I'm following the red curve, and I end up on the T2 isotherm. That's the way I drew it. Okay? Notice then that in the adiabatic expansion of the gas, the temperature of the gas went down. Because we started out on the T1 isotherm, and we ended up on the T2 isotherm, and the T2 isotherm is below the T1 isotherm. Okay? So in the adiabatic expansion, the gas's temperature had to go down. Adiabatic does not mean isothermal. Right? Absolutely does not mean isothermal. It means, adiabatic means, and it only means Q equals 0. And anything that is a consequence of that fact. Now what if we did this in reverse? What if we started out with a bigger volume and reduced it, i.e. compressed the gas adiabatically, so don't let any heat go out? What has to happen to the temperature of the gas? It's got to go up, right? That's just following the red curve but going backwards. Yes? Temperature's got to go up. In fact, it's going to be actually probably pretty dramatic. So here's another demo I usually show in intro physics. An adiabatic compression of an ideal gas. The ideal gas will be air from the room. Cylinder, hollow in the middle so air can get in. I will take a little bit of cotton wool. The key is to get a very little bit. This usually takes a couple of tries before it works. We'll damp it down in there. Towards the bottom. Then we'll just take a plunger. Tighten it on there. And push it down real fast. Fast enough that there isn't any time for energy to be exchanged with the surrounding air as heat. I.e., it'll take it back. I like to put it on the floor, put my feet on that wooden support so that, sorry. So, make sure you can see this thing. We may have to try it more than once. No, never mind. Do you see the flash? Now, so what was happening? We were compressing the gas. We were doing it fast enough that there was no Q going out. Adiabatic compression, going up the red curve, temperatures going up. Probably going up pretty dramatically, because we're compressing it a lot. Okay? In fact, cotton will spontaneously combust if the temperature of the surroundings is at least 400 degrees Celsius. So I must have been able to get it to at least that, because it ignited, right? This is an example of what in the old, the days of fire, when fire was high-tech, you had to have a way to start a fire, so you would have a little adiabatic compression kit with something that could burn easily, tinder, kindling, and some way to compress air. We call it a fire starter. That was high-tech in the day. You can smell the burn.
Smell the science.
Okay. So that's an adiabatic compression. Okay. All right, now we're going to be using that. And what I want to do next is I want to do an example problem. Let me state it, and then we'll take a break. Well, no, I don't know. Why would I do that? Let's take the break, and then I'll state, and we'll do an example problem in which we have an adiabatic. In this case, it'll be an expansion of an ideal gas. Okay? Okay, so let's just take the break.